Deep beneath Chihuahua, Mexico, the Cave of Crystals holds geological structures that defy standard proportions. Grown in a submerged, mineral-rich subterranean cavity, these columns of calcium sulfate stretch over 30 feet in length and weigh up to 50 tons. For hundreds of thousands of years, they sat in a stable, heated, fluid environment. Then, commercial mining operations pumped the water out of the cave. Almost immediately, the crystals were exposed to an ambient atmosphere of humid, 60 degrees Celsius air. Today, these structures are experiencing acute structural failure. Their transparency is clouding over, and the surfaces are actively fracturing and splitting apart under their own weight. To understand exactly how fast the damage is occurring, researchers initiated a multivariable laboratory experiment. They needed to isolate the precise environmental triggers driving the decay. Predicting whether these monuments will survive requires moving past subjective visual observation. We have to map the exact kinetics of their dehydration down to the molecular level. The baseline material of these massive structures is selenite. This is the highly transparent, macrocrystalline variety of gypsum, composed of calcium sulfite dihydrate. Selenite is exceptionally fragile. It ranks at merely a 2 on the Mohs hardness scale, making it soft enough to scratch with a fingernail and highly susceptible to environmental shifts. The primary threat to the Naica crystals is not external mechanical wear or chemical erosion. The threat is an internal crystallographic phase transition. In response to atmospheric exposure, gypsum begins to dehydrate into a metastable phase known as basanite. Chemically, this transition strips exactly 1.5 water molecules away from the original calcium sulfite formula. The loss of these water molecules is the mechanical trigger for the structural collapse of the world's largest crystals. This 3D atomic model of the gypsum lattice shows water molecules forming flat, stable sheets along the cleavage plane. When dehydration triggers, water escapes. Surrounding structures immediately contract into the empty space. Transitioning to basanite, the remaining water reorganizes into isolated vertical channels. This atomic reorganization generates immense internal shear stress across the entirety of the crystal lattice. Macroscopically, this stress manifests as millions of microscopic fractures. As the planes pull apart, the selenite loses its smooth, glassy transparency and turns opaque. This catastrophic failure occurs without a single molecule of calcium sulfate dissolving. The chemical backbone remains intact. Dehydration rewrites the crystal's architecture, creating an inherently unstable internal structure that destroys the formation from the inside out. To map this destruction, researchers needed a way to accelerate and isolate the specific environmental triggers of basanite formation in a controlled setting. They placed clean selenite samples inside sealed reactors and pumped in specific gases: standard air, carbon dioxide, methane, and nitrogen oxides. They varied the environmental state, either exposing the samples directly to the gas or submerging them in a saturated liquid solution. They controlled the thermal parameters, running parallel tests at 25 degrees Celsius and an accelerated 60 degrees to mimic the heat from the cave's natural magmatic intrusion. This diagram represents the experimental matrix. The final parameter was time. Samples were analyzed at 1, 3, 6, and 12-month intervals. Multiplying these variables yielded 64 distinct scenarios. Testing each allowed the team to try to predict transition under specific conditions. This exhaustive matrix allowed researchers to isolate thermodynamic variables from chemical weathering and identify the primary driver of the decay. Subjective visual observation of the samples isn't rigorous enough. The researchers needed a hard metric to quantify the exact degree of damage, termed the relative amount of basanite, or RAB index. The first diagnostic tool used to calculate a sample's RAB score is infrared spectrometry. This technique probes the distinct vibrational modes of the sulfate ions within the crystal. The researchers targeted one highly specific frequency, the emergence of the nu 3 sulfate vibration. This animated plot of an infrared spectrum shows a distinct signal forming at the 1180 wave number mark. This peak is diagnostic of basanite. It is entirely absent in the spectrum of pure gypsum. Detecting this vibrational shift allows researchers to identify structural decay at the molecular level, long before the crystal shows any macroscopic signs of damage. To corroborate the infrared data, the team utilized a secondary, more rigorous verification method, grazing incidence X-ray diffraction. Lab-based X-ray diffraction scans the physical surfaces of the samples, precisely mapping the geometric distances between crystallographic planes. This X-ray diffraction pattern displays the baseline control. A healthy gypsum plane produces a main reflection at exactly an 11.6-degree angle. Degradation is indicated by a new reflection signal at 14.8 degrees, corresponding to the spacing of the basanite plane. To verify the absolute faintest traces of decay across the grid, the researchers took their samples to high-resolution synchrotron radiation facilities for advanced diffraction analysis. Combining the infrared detection frequencies with the X-ray diffraction angles yields a definitive semi-quantitative RAB score for every single one of the 64 samples. By stripping away human visual bias, this multimodal analysis provides an unassailable mathematical model of how and why the structures are degrading. Given the location, a logical hypothesis assumed by many was that acidic or carbon-rich mine gases from heavy industrial machinery were driving the rapid degradation of the crystals. Chemically, scientists expected that high concentrations of carbon dioxide and nitrogen oxides in the mine shots would cause immediate chemical dissolution or carbonate replacement on the crystal surfaces, but the X-ray diffraction analysis revealed a massive anomaly. The data detected absolutely zero calcium carbonate formation in any of the samples. Even when samples were sealed in extreme, high-concentration carbon dioxide atmospheres for 12 continuous months, the expected chemical reactions simply did not occur. The deterioration of the crystals is strictly a thermodynamic issue of water loss. It is not a chemical reaction with airborne pollutants. Industrial pollutants in the mine are hazardous to human lungs, but they are a red herring here. They are completely irrelevant to the primary mechanism destroying the selenite. The data across the RAB scoring matrix identifies the most significant factor in the decay, a standard gaseous air atmosphere. This chart synthesizes the relative amount of basanite scores. Standard atmospheric air produced significantly more degradation than any pollutant gas. High temperature and direct gaseous exposure drove the most accelerated rates of phase transition over 6 and 12 months. The physical reality of this finding is brutal. Long-term exposure to ambient, breathable air physically rips the crystal surface apart from the inside. As the internal lattice shrinks to form basanite, the planar layers of the crystal lose their structural cohesion. Massive sheets running parallel to the primary cleavage plane detach. A once flawless translucent surface aggressively fractures and splinters apart under immense, invisible tension. By draining the water and introducing ambient air into a sealed system, human intervention initiated a structural collapse that will continue until the crystals are lost. Preserving Naica's giant crystals requires extreme measures. We either have to engineer a way to totally isolate their local atmosphere, or we have to reflood the cave, returning these monuments to their ancient, submerged state.